This video is a speedrun final prep session for the Kp Equilibrium constant topic in AQA A-level chemistry. In it, I've explained things quickly and without practice questions, so if you do need more detail or some practice for yourself, be sure to check out the videos in the full playlist. When a reversible reaction occurs in a closed system, in other words, no matter and no energy are added or taken away, then the reaction may reach a stage called equilibrium. At equilibrium, both reactions are occurring at the same rate, and the concentration of all reactants and products in that reaction is unchanging. This does not mean that they are the same as each other, just that they're not increasing or decreasing. And in fact, there's a whole chemical industry built around trying to maximise the amount of the product while minimising the amount of reactant left over. While you can write a Kc equilibrium constant for gaseous systems, in order to do that, you need to know the volume you're working with. More typically, for gaseous systems, we use Kp, which is a mathematical expression used to describe the position of equilibrium for a reversible reaction with gaseous reactants and products. It's based on partial pressure rather than concentration. Similarly to Kc, we're putting the products on the top of the fraction, and we're also using the coefficients from the symbol equation as the powers. But differently to Kc, we're no longer talking about concentration. So brackets, if you use them, cannot be square, and we also have a p or a pp, and that can be inside or outside of the bracket. The simplest type of Kp question would just give us values for partial pressure and ask us to substitute these in. So we would end up with something like this. Like Kc, there isn't one set unit for Kp, and we need to look at the units that we've been given and the different numbers of moles on the left and right of the equation. So here we've got 4 sets of kilopascals on the top and 3 on the bottom. So once we cancel those out, we're left with an overall unit of kilopascals, but this won't always be the case. A gas will exert a pressure based on how many moles are present, regardless of the identity of that gas. Therefore, if we know the total pressure of a gas mixture and we know what proportion of the mixture each gas is, which is what we call the mole fraction, we can assign a partial pressure just to each individual gas. So if I look at the molecules that I've got, 50% of those are the red, so my mole fraction there is 5/10, but I simplify it to a decimal of 0.5, and then 20% blue and 30% green, and those are all going to add up to be 1, which is 100%. And then I multiply each of those mole fractions by my total pressure to find out that the partial pressure of the red is 75, and the blue is 30, and the green is 45. And again, those will all add up to be my total pressure. Just like with Kc, you're incredibly likely to get an equilibrium question where before you can use that expression, you need to work out what the equilibrium moles of each substance are. So you may need to construct an ICE table, or they're sometimes called RICE tables if you have ratio at the start. But I is for initial, C is for change, and then E is for end or equilibrium. A typical exam question will tell me how many moles of the reactants I started with and not mention the products at all, so we assume that they are 0. And then it will also tell me at equilibrium either that one of the reactants has changed, or it'll give me the moles of the product now. And based on this, I can work out what the change will be. So then I'm going to use that together with the coefficients in my symbol equation to work out what the change will be for the other species in this reaction. So my oxygen is only going to decrease by half a mole because that and the sulfur dioxide are in this 1:2 ratio, whereas the sulfur trioxide will also increase by a whole mole. So that gives me my equilibrium moles. But remember, at this point we're not finished. We need to convert these back into partial pressures before we can put them into the expression. So I add up the moles of all of those species, and I get a total of 5, and then I can work out a mole fraction, which in each instance I'm going to simplify to be a decimal. And then if I know what my total pressure is, then I can take that from the question and multiply it by this mole fraction to give me partial pressures for each of the substances. And then I can put that information into my expression. Remember, if they ask you to write an expression, they mean write this thing for Kp, including the names of the reactants and products in there, and then I can substitute in my numbers, and then I get a value and I can work out my units like I did before. Just like you did with Kc, you should be able to describe how changing temperature affects the position of equilibrium, the yield of the desired product, and also the value of Kp. So here I'm going to start off by saying the system shifts to counteract the increase in temperature. Then I'm going to say, well, I can see that the forward reaction is endothermic from the enthalpy value that they've given me there, and therefore that forward reaction will be favoured. That means that the equilibrium will move right, and that means that there'll be more products. And if there are more products, and remember products are on the top of my expression, then the value of Kp will increase. Then if we think about pressure, we start off by saying that as we increase pressure, the system will shift to counteract the increase in pressure. And therefore here the forward reaction will be favoured because there are fewer moles on the left-hand side of the equation. And therefore the equilibrium will move right and the yield will increase. But we now also need to think about the value of Kp. If I just throw together an expression for Kp and give you some values for a particular equilibrium, we can come up with a value for that equilibrium under that pressure. We started out with partial pressures which added up to 100 kilopascals, and therefore our initial value for Kp is 0.15 kilopascals to the -1. Now, if we increase the pressure, we're going to make more of C, but you also have to remember that as well as the mole fractions adjusting, the total pressure has increased, and that's going to have an impact too. So if the pressure change leads us to having 0.1, 0.1 and 0.7 moles of each of our chemicals, and our new pressure is 420 kilopascals, then when I use the new partials, I get a new value for Kp that is still 0.15 kilopascals to the -1. So you don't really need to be able to prove this, but you do need to know that changing the pressure, although it changes the position of equilibrium and the yield of C, it doesn't change the value of Kp. Catalysts don't have any impact on the position of equilibrium, whether that's an equilibrium with solution or an equilibrium with gases that you've learned about in year 13. And the reason for this is that even though the catalyst speeds up the rate of reaction, it speeds up the forward and reverse reactions equally. So it doesn't have any impact on the value of Kp because it doesn't have any impact on the position of equilibrium. So to summarise that, temperature will change the position of equilibrium and therefore yield and Kp. Pressure will change the position of equilibrium but not Kp. And catalyst will not change either. Thank you very much for watching, and I hope that you found this brief summary of the Kp equilibrium topic useful. If you have, then don't forget to like and subscribe for more A-level chemistry videos coming soon.